Now, friction in machines is also very common, and we're going to analyze a couple of these here. What we got here is a handheld rivet machine or riveter. And then what happens is when you squeeze these handles, it puts some force down in here. So let's just zoom in over here, and you can kind of see, well, I hope, the way this thing works. Like most of these problems, if you can figure out how it works, it really helps in trying to figure out how to solve for the answers that they're looking for. But when you squeeze these two handles, it kind of rotates this part around point C here, and then D pushes downward on the rivet part, and this is where the riveting actually takes place. So what we're looking for is what's going on right there at D. So let's zoom out here and let's see if we can analyze this. All right, I'm going to draw a free body diagram of just the handle and see what we can find. The handle has a 60 Newton force pushing down. It's got a dy coming up like that. And there's going to be reaction at C. I'll put Cy and Cx. I think I'm going to go the other way on that Cx. And then where there might be some friction will be right there, and I'll call that dx. Okay, what we're looking for is what is the pushing force downward. So let me just zoom out here, and we'll just say some of the moments about C might give us some indication. So sum of the moments about C is equal to 0. So here I have 60 times 205 in millimeters minus dy, and it's got a lever arm of 6 millimeters, minus dx. Now, in this case, it is a slipping scenario. dx is equal to mu dy. So I'm just going to, instead of even put it in there, I'm just going to say mu dy is times, and it's got a lever arm of 17 millimeters, and that's equal to 0. I know my mu is equal to 0.3, so I can solve this for dy is equal to 1008, and that's in newtons. So the mechanical advantage here, is equal to the out over the in. In this case, it would be 1108 divided by 60, and so that would be equal to 18.5. So that's a pretty good mechanical advantage, even with friction. How is it without friction? Let's say that the friction went away, and so that in that case, this term would go away. In other words, dx goes away, and so all we're doing now is sum of the moments about C. So sum of the moments about C is equal to 0. So here I got 60 times 205 minus dy times 6 is equal to 0, and dy here then would be equal to 2050 newtons. And so the mechanical advantage would be, let me get an eraser, mechanical advantage would be equal to 2050 over 60, and that's equal to, well, let me put it down here. That's going to be equal to 4.2, or almost 35. So clearly you have a much greater mechanical advantage without friction than you would with friction, which you might expect, of course, that friction is going to take away some of your effort or whatever. But anyway, sometimes it can be quite significant. This is another scenario where we're doing some work, if you will. This is what a machine often does. This is actually a friction problem from chapter 8. But what we got is a pulling force here that is trying to lift up a crate. And it's using some friction right there between there and there to help you lift it up, or to enable you to lift it up. So in order to solve this problem, again, this is quite a system here. So let's just talk about some things that we know. If there is an mg going down, If I define my system as this whole system, I know that P is equal to mg. So right off the bat, I know that the P, the pulling force up, is equal to the weight. The next thing to do is to try to find out what as much as you can about some other different things. So I'm going to make sure I understand what's happening at the crate. So if I draw a free body diagram of the crate itself, I know that it has an mg. Those two contact forces are going to be pushing in like this, A and B, and they will have some friction going this way. Again, if this is a maximum situation where I'm looking for potential slip, I know that this is going to be mu A and mu B. It looks like symmetry applies here, so I think you could probably suggest that this side is equal to this side. This is going to be equal to that. These two together are going to be equal to that. A is going to be equal to B. Those are the kinds of things you'd look for in symmetry. Next thing I'd look for is what's happening at this joint right there. Now this, you should recognize that this is a two-force member, and both of those are two-force members, and this is a two-force member. So let's just go ahead and draw point H as a free body diagram. I know that lifting up is going to be P, which is equal to mg. I don't know what that is. I guess it's 150 times 9.81. I guess we didn't solve that yet. But in order for this joint, we would use the method of joints in this case, where I know that these are going to be two-force members, two-force members in pushing back toward that joint. And this is going to be a 30 degrees. And you just use method of joints rules in order to solve what is going on in EH and or FH, if you need both of those. Then, lastly, you kind of have to look at what is going on in this larger member, which is ECA. So let me just draw the free body diagram of ECA. In this case, I have that EH pushing up in the same manner that it is pushing toward point H here. So this is EH. And this one has this is equal to a two-force member. And this one's equal to a two-force member. And then what happens over here at A, those things have to transfer equal opposite from here to here. So let's put A here. And then let me zoom out a little bit. And then this will have the mu A looking like that. So you have three free body diagrams to work through. I'm not sure, again, there's any specific way to do it, but I like to work from places where I know something. And this is the two places where I know something. I know something about this one because I know that P, and I know something about this one, or at least I know some relative stuff. I wouldn't start here because this is, it's just more difficult. You don't know any of those forces quite yet. The next thing is friction brakes, and this is a pretty common, very common scenario as well. And so what we have here is a disc that's being rotated with a moment, with a torque. It's rotating here, and we want to slow it down or keep it from moving. If it's moving, then we want to slow it down. If it's not moving, then we want to keep it from moving. And the way we're going to do that is we're going to apply some force here, which is pinned right here. It's going to be pushing up on that disc, and there's going to be some friction right there at point B. So let's draw the two free body diagrams that make some sense here. There's no weight to worry about here, but what we do have is a normal force right there, and we'll call that normal force of B. And it has this torque going in this direction. In order to keep this torque from going or moving, and we have to have a friction force that is going in the opposite direction. So I'll say that this is going in that direction. That's going to be the force of friction. Again, this is the slip scenario, so I could say that this is equal to mu B. Those forces transfer equal opposite to the lever, or to the handle down here. So this one will have B going down, and then mu B going this way. All right, let's analyze the disk first. If I sum the moments about the middle, I can say that I have a 5 Newton meter moment going in the negative direction or the clockwise direction plus mu b times its lever arm of 150.150 going in that direction is equal to 0. Now mu is equal to 0.3, so that's minus 5 plus 0.3 b 0.150 is equal to 0. So I can get b here is equal to 111.1 newtons. Now that gives me enough information then to transfer over to here. What we're looking for in this case is what is P in order to make this stop. That's the I guess what we're looking for is how much is that P. All right, over here then, let's go down here and we're going to sum the moments about point A. Let me draw the reactions at point A. There's probably some AY and maybe some AX here. But again, I don't need to worry about those reactions at A unless it's asked for. But in this case, I'm going to sum the moments about A because that seems to be a logical point of rotation. And I can probably solve this for P. So let's try that. P times the full lever arm of 0.4 plus 0.2 minus B, and it's got a lever arm of 0.2. And this is what many students forget, is this friction force. This friction force also has a lever arm. In other words, B is going in this direction, and mu B is also going in that direction. So I'll say minus mu B is also there, and that is 0.05, and that's equal to 0. I've already solved for B, and I have mu is equal to 0.3, which I can also put in there. Solving that for P, I got that is equal to 39.8 newtons. Okay, let's go back to the question. What question were we looking for? It says determine if the brake can hold the wheel stationary when the force is applied. How about if I apply 30 newtons? Can I hold it if I only apply 30 newtons? And the answer is no, because I need 39.8. If I apply 70 newtons, then surely I have enough, because I only need almost 40 newtons to make it stop.